in the previous lectures, we've seen a general introduction to this course, the layout of a microscopy lab, and briefly touched upon various components and saw the ray diagram of the microscope. Now, let us understand each of the components one after the other. Today's lecture, I'll be focusing on electron sources. So when I talk about electron sources, it is what you have in this upper half or in the very top portion of the microscope. Here is the lanthanum hexaboride filament operated TEM, the JEM 2100, and as you can see, this portion which is enlarged and shown in this red border is where your source is. So this is called as actually the electron gun, and there are several components which form the electron gun. When I talk about the different kinds of electron sources in transmission electron microscopy or in scanning electron microscopes, we commonly have two kinds of emitters. Let us have a look at what these emitters are in the next slide. So as I was mentioning, the two common sources that we have for electron emission are the thermionic sources or the field emission guns. Now when I talk about a thermionic source, it is very much similar to something which we are very familiar with, the incandescent bulb. So here in a thermionic source, the principle is you actually have a very fine filament, typically a tungsten filament, and then you really heat it to a very high temperature by passing an electrical current. So because of the resistive heating, you not only have emission of light, but at very high current, when you overcome the work function barrier, you also have the emission of electrons. These electrons are now converged to a point and you focus them. So if I want to converge a beam of electrons that are emanating from a filament, naturally the construction would require that I have some kind of a lens there. This lens should be able to control the electron beam. So the general construction of an electron source is you have a filament, which is the cathode, and you have something to converge. So you have something called as the Wenelt grid, and you also have an anode. So essentially, having a cathode, having a tungsten filament, having some source similar to an incandescent bulb is not enough to emanate the electrons and converge them to a point. To have all this functionality, you would want to have some kind of a lens which converges this to a point. So let us have a schematic layout and look at the components of a thermionic source first, and then we will see how a field emission gun looks like, and we will draw a comparison between these kind of sources, and we will try to understand what effects this has on the quality of image and the resolution you can achieve in a transmission electron microscope. So let us first look at the layout of a thermionic source. Here is how the thermionic source and the cathode part or the Wenelt grid looks like. I will show you a schematic from the microscope that I have shown you a demonstration, that is the lanthanum hexaboride filament 2100 TEM. Here is the image taken from the user manual of the 2100 microscope. So the components you have are, you have the base. Remember in mind, to give a better understanding, the layout in the microscope column is reversed here. So it is pointing, so this is the way up in the TEM. So just for convenience and to understand the components, we have turned this upside down. So this base or what you see here is actually at the top of the microscope column. You have a small filament here, and as you can see, this portion acts as the cathode, and you have a cap here. So you can unscrew these two components and remove it. It is like the way you place a small incandescent bulb in the filament holder or in the bulb holder. You similarly have a base and a filament holder here, and you fix it inside a conical shaped Wenelt cap, or sometimes we call it as the Wenelt grid, and this goes into the top part, and on the other side of this you get the anode. I will show you another schematic very shortly, but let us see how a real filament looks like. Here is the filament that we have inside a lanthanum hexaboride TEM. This was in fact taken out from our own microscope here. So this is from, I think, a company called Denka. But what you have here is the posts you see here are placed here, and this is the rhenium wire or a tungsten wire, and on top of this you have a tiny lanthanum hexaboride filament. If I look at a schematic of this, here is how it actually looks like in the microscope. So I have the filament and this whole assembly, which looks like this part, and I start applying some kind of a bias on the Wenelt grid. The whole objective of this is, from the cathode to have an emission, I have the oppositely charged anode here, and I also have a Wenelt grid. It is typically a self-biasing one in a lanthanum hexaboride gun, but in the other construction of a field emission gun, you would have two anodes. I will not go there yet, but let us understand this one first. You apply a small bias, or you do not have any bias on the anode. The anode is maintained at the earth potential or at the ground potential. So you are extracting electrons from the filament. So typically you start this from 0 to for example 700 volt, or you go even up to 1500 volt or so. You might start seeing some kind of an emission. So the electrons are coming out in all the directions. To converge them to a point and to have this along the trajectory of the electron beam path of the microscope, or to have it along the optic axis of the microscope, you want these electrons to converge, and that is why you have this Wenelt grid and the anode here. Remember that once this emission happens, beyond the gun, you are accelerating the electrons in the path of the electron microscope depending on the accelerating voltage you use. It can be 60 kV, 100 kV, 120 kV, 200 or 300 kilovolts, or even it could be a high voltage electron microscope. It can go even up to 1.3 million electron volts. But depending on how this goes into which instrument, the essential construction of a thermionic gun is the same. You have this kind of a Wenelt tool or a Wenelt grid, and then the filament goes into this. You have an anode on the opposite side, which is typically maintained at the ground potential, and you start extracting electrons shortly, and then you focus them or converge them to a point. So let me show this on the ray diagram of the microscope, how this looks like and what exactly is happening when your emission happens in a thermionic filament. So in a thermionic emitter, as you can see, if I start extracting the electrons from the filament, what happens here is you start from a current which is very low, and then as the electrons start emitting here and the charge gets accumulated, it gradually becomes slightly negatively charged. And what happens is, at this point, you actually have to overcome a sort of a barrier or an electron cloud that is formed in front of the source to have a sustained emission. So that is where you have this optimum bias. And if I now look at the flux of the electrons emanating from such a filament, you can always write this with an equation which, so if I say the flux emanating is J, and if I have an exponential function like this, so this looks like an Arrhenius type of an equation. This is called as the Richardson's constant. You have the flux emanating as a function of the temperature, the work function, and the temperature here again, and this is the Boltzmann constant. So, typically you would expect this curve to look like an exponential function, but because I was just mentioning that as a small partial negative charge builds up here, you would have this appearing with a small kink where you have some critical current density beyond which you have a sustained emission. Now, after you have this kind of an emission, if you look at the ray diagram of the microscope, let us see what happens here. So, here is where your electron gun assembly is, and I have shown that the path of the electrons are converging at a point here. This point is actually called as the first crossover. This is an extremely important thing here, because this crossover point can act as the object for the subsequent condenser lenses that you have in the electron beam path. So, just below the electron gun, I have the condenser lenses, which is also a part of the illumination system of the microscope, and this electron lenses are actually electromagnetic lenses, and by simply changing the strength of these and also changing the strength of the first condenser lens here, I can have a nice interplay between looking at where the crossover point is. Now, what happens here is, by making this first condenser to have the crossover point at the back focal plane of the second condenser, I can control whether my illumination or the electron beam is going to have a sort of a converged probe kind of a path or a parallel illumination. So, if you understand the physics of this, if I have my second condenser lens here and my electron beam from the source is emanating to be at the back focal plane of the condenser lens. So, if I have a point source here and this is coinciding with the focal plane of the second condenser, the electron beam that comes in would have a parallel path, and just depending on whether it converges here or here, I can always control whether I have a sort of a conical illumination, or with the combination of these I can also form a probe and converge it to a very small point. So, when you have a series of condenser lenses, by converging the source to a point and allowing it to be at one of the focal planes of the second or the third condenser lenses, by the combination of these condenser lenses, I can really get a very fine probe, or I can get a parallel beam illumination. And the kind of the illumination that I use in a microscope would actually help me choose the different modes of operation I want. For example, if I am using techniques that use parallel beam illumination, I might want to have a beam which is spread over. Now, why is this important, and how does a thermionic source matter? One of the important parameters is this crossover point for a thermionic emitter is not extremely fine. To have a better crossover and to have a very small probe, you would want to go to the field emitters. Let us now see how the thermionic emission functions. We will have a look at how a thermionic emitter emits the electrons along the microscope column, and then let us see how a schematic construction of a field emission gun is and how that looks like. So, if I look at the thermionic emission, I have to overcome the work function barrier. Work function is defined as the energy barrier that prevents electrons from escaping a material. Once I overcome this barrier, I have a sort of an emission which follows the equation that I just showed you, the Arrhenius kind of an equation. The current density can be given by an equation like this. And then one important parameter is, when the temperatures actually go very high, you would want to have a material which is sort of a refractory material, and typically you use tungsten. But on tungsten, you would not have a very low work function. You could still have pure tungsten emitters as well, but you use a material like lanthanum hexaboride or cerium hexaboride. These crystals typically have a low work function, and it is established that the 110 plane, the crystallographic facet of 110, is a direction which has enhanced emission. So the construction that I showed you in the previous slide, which is like this, you have the lanthanum or a cerium hexaboride crystal. Nowadays, people are trying to replace this with carbon nanotubes also for having some kind of an electron emission. That is an entire field of research which I will not go into at this moment. But to give you an idea that on the tungsten filament, you have a crystal which sits like this. Bear in mind, even to the visible eye, or when I take an optical image, the crystal is still visible with a sharp facet which is along the 110 direction of the lanthanum hexaboride crystal. And if you can see, this particular size of the filament that you have plays an important role on one of the parameters which is called as coherency, in particular spatial coherency, which I will define when I draw a comparison with a field emission gun. So let us have a look at how the thermionic emitter looks like. I will play a small video here. So you can see that when I switch on the emission in a microscope column, I do not see anything. I am trying to record the image I get on a fluorescent screen here, and at some point I start seeing the whole area is illuminated. You just saw that this illuminated region, there was a small jump here. Let me just play that little change once again for your reference. I see there is some bright image that I form here, and then it slightly reduces, and there is some kind of an adjustment that happens, and then I have more bright sustained emission on the screen. If I now plot this current density as a function of time, I had the small jump and then I had the sustained emission. This was the graph that I showed you on the other screen as well some time ago when I defined this equation. I have to overcome this critical current density. That is because of the kind of the shielding layer that is formed with all the electrons that are extracted and right in front of the tip, and beyond this I have a sustained emission. So as you can see, this is a very similar principle to an incandescent bulb. I just heat it up, and by resistive heating I get emission of electrons. Bear in mind, this green color you see here on the fluorescent screen is because the electron beams, which are not visible to our naked eye, which are not within the visible spectrum, are striking a fluorescent screen, or they go and strike a CCD camera, and because of the phosphorescence from the material that is there on the screen, you start seeing this color. In fact, when you have some kind of field emitters, you could have a different kind of a material, and you might see this in a sort of a purple color. I will try to see if I can get an example of emission from a cold field emitter. But please bear in mind that this constant bright current that you see and that is spread over this large area, you would actually have a sustained emission in a thermionic emitter. Please bear in mind that this illumination that I have spread across a large area, I can now converge this or I can spread this by controlling something called as an intensity knob on the microscope console. Having seen this, we will look at the next kind of an emitter, which is called as a field emission gun. If I look at a field emission gun, like I was mentioning a while ago, you have the Venel grid, you have the cathode, and then you actually have a very fine tungsten wire tip, and which is coated typically with a kind of a zirconium oxide, and then the fine needle is positioned within the filament holder area, and you have two anodes here. The function of these two anodes are, you have an extraction anode where, like in a field emission, in a thermionic emitter, you wanted to have some electrons emanating, and then the accelerating anode which boosts these, and you also want them to converge to a point. What happens here is, your filament size is much finer than a lanthanum hexaboride crystal. If you remember, I was mentioning to you that it is visible to the naked eye. If I look at a scanning electron micrograph of how a filament tip in a field emission gun looks like, this is an image taken from the famous textbook from Williams and Carter. You have an extremely fine tip. Typically, the tip radius here is less than 20 nanometer or 50 nanometer, and this goes into an assembly which looks like this. Here is a schematic of a field emission gun. This is typically used in a Schottky field emitter, or even a cold field emitter has a similar construction. So essentially, you have initially some extraction that you have in this anode, and then the accelerating anode is in the microscope column, where you are having this go along the accelerating voltage of the microscope, but you have the first anode and the second anode and the crossover which is at a very fine point. So what you have here is, combining the fields of both of these anodes, you are actually having this behave like a lens, and in comparison with a thermionic emitter, the field emitter already, before it is going into the condenser of the electron microscope, it is focused to a very fine point. So in fact, you can call that, unlike a physical source from where you have the emission happening like an incandescent bulb in thermionic emitter, here you sort of have a virtual source which is beyond the field emission gun. You have the electron beam focused to a very fine point, which is typically coinciding close to the backfocal plane of the second condenser lens. And with this kind of a combination of multiple anodes and addition of a magnetic field lens, you have much better beam control. You can make the beam converge to a much finer point, and you have increased brightness. So if I look at the energy diagram of how electrons are extracted and understand the principle of a field emitter in a bit more detail, you have the following. The idea is, at the very fine tip, I apply a very high field. Typically, when I have even the field of the potential of the order of 3500 volt or so, or typically the extractions start from around 2.7 kV and you go up to 3.5 to 4.5 kV depending on the mode that you are operating in. And if my tip radius is less than, or if it is in the order of tens of nanometers, you can see that my electric field is extremely high. It is of the order of a few 10,000s of volts per nanometer. And what happens here is, when I have such a high field being applied, and I also have the effect of the anode that is kind of lowering my work function barrier, this particular anode which is present in front of the fine tip. So if here is my cathode and I have series of anodes here, this anode is actually kind of helping me lower the work function barrier as well. This is called as actually the Schottky effect. So in a field emitter, because of the Schottky effect, by having a combination of two anodes, I am kind of lowering the work function barrier. So in a thermionic emitter, if I had to extract electrons from within the filament into free space, I had to overcome this work function barrier, and with the addition of the anodes here, I can kind of lower the work function barrier a little, and I have a sustained emission at slightly lower potentials than in a thermionic emitter. So what this does is the anode not only focuses the emitted electrons to a confined path and to a very fine spot, but I also have lowering of the work function barrier, and I have a better control in a field emitter. So if I look at the advantages of this and in a little more detail, when I have tungsten tips of a very fine radius, I have a very high potential, and this also overcomes the work function. You not only lower the work function barrier, but in a few cases you would also allow the tunneling of the electrons. What do I mean by tunneling? It is a kind of a quantum mechanical effect where if I bring the anode extremely close and I apply such high fields, so if I bring this gap, so within a Venelt grid in a thermionic emitter, we have seen that the gap here was in the order of a few millimeters or a few hundreds of microns. But in a field emitter, if I bring it even closer to the order of half a micron or even lower, let us say even a gap of 200 or 300 nanometers, what happens there is when such a high field is brought close to a tungsten filament which is very sharp, the way you have in a scanning tunneling microscope, you have electrons just going out without overcoming the work function barrier, and you can have a sustained emission. But bear in mind, in order to have this happen, you need to have an extremely good vacuum. So if in the ultra high vacuum systems, let us say I have a vacuum of, let us say, of the order of 10 to the minus 8 millibar, you would want to have this even better than 10 to the minus 9 or even lower to have the tunneling happen. Also, one of the consequences of such high fields and even within low vacuums of 10 to the minus 7 to 10 to the minus 8 millibar, the filament tip is so fine that you cannot avoid the formation of some kind of an oxide layer on the tungsten filament. So you would naturally have some kind of effects of formation of an oxide layer, and if you have an oxide layer on a conductive tungsten filament, bear in mind that the oxide can also have some kind of a charging and flashing as well. So this will kind of reduce the brightness or the flux that is coming out from a field emitter. So to overcome these, you would want to have a feedback loop. So I am kind of mixing up the constructions or the principles of a thermionic or a Schottky FEG and a cold field emitter, but you would want to have a pristine surface on the filament. If possible, you would want to have sort of a flashing of the filament, and you can have tunneling of the electrons. Now, within the field emitters also, there are two kinds of emitters. You would have a thermal field emitter where the tip can be heated in a slightly poorer vacuum, and in a very controlled fashion, you kind of raise the potential on the anode such that you have extraction of the electrons. In the microscopy terms, you can call it as a warm start or a cold start. So what do I mean by a cold start is, if I want to achieve a potential of around 2.7 to 3 kilovolts to extract electrons from the tungsten filament and then form a crossover or form an image of the probe and converge them into a very fine point, I will do this at a very low rate. That is, I raise the potential at, I don't know, 0.1 volt per second or even lesser, such that I reach this 2.7 to 3 kilovolt in a duration of about 2.5 to 3 hours. In the very old days, on the older instruments like the Philips CM20 or CM30 series, you were manually turning the knobs. With the digitization and having feedback controls, you can now do a warm start in a very gradual way. But if you are not having a good control on increasing the potential gradually, what happens is you might actually fracture the tip of the tungsten filament and you might actually lose it out. So, in a thermal field emitter, with a gradual increase in the potential by doing a warm start, you can have sustained emission at a potential slightly lower than the work function barrier. And because you do this gradually and you maintain the current or the emission current from the field emitter reasonably well, the stability of a thermal field emitter is not too bad in comparison with a thermionic gun. And if I look at the other kind of a filament or the cold field emitter, I was mentioning that you have to maintain an extremely high vacuum and you want to have tunneling of the electrons. You in fact bring the anode a little more closer to the tungsten filament to have sort of a electron tunneling effect, and you do not go past the work function barrier. But the challenge here is, when I am doing this, the operating voltages in a field emitter would go slightly higher. You would go up to 7.1 or 7.5 kilovolts even, and you would have the same 2 anode construction here as well. And what you do is, once you extract the electrons, you are also suppressing it by using the other anode, and you control the beam currents in a much controlled fashion with a feedback loop. Now, the challenge here is the vacuums, although are ultra high vacuum, there is a chance that when you go to these high potentials, if you do not have a good feedback control, the filament tip can get fractured much more easier. And if you have this, your stability of a cold field emitter was not extremely good in the mid 90s to, let us say, the digitization that happened, let us say, around 2000 or 2005. From somewhere around 2000 onwards, in fact, I can say the manufacturers such as Hitachi and JEOL have successfully mastered, and very recently even Thermo Fisher has come up with the field emitters, cold field emitters. Thanks to the modernization and having a feedback loop, you can do what is called as flashing of a filament. So, essentially, if I extract electrons in a cold field emitter, over a duration of about 3 hours or so, I might have a very good beam current, but then this gradually drops down, and I might end up with sort of an oxide layer formed, and we do something called as flashing of the filament. What you do here is you go much beyond this 7.5 kV. You could go to a very high pulse over a very short span of 8 seconds or 10 seconds, and you kind of sharpen the filament tip in situ within the filament assembly, and then or within the FEG assembly, and you can redo the emission and imaging again within the microscope. So, with this, the lifespan of the filament is kind of naturally, when such a technology is coming into the market, people would have done all the homework in such a way that the overall lifespan of a cold field emitter, where you are not doing a warm start. So, the main difference between a thermal FEG and a cold field emitter is, once you switch on a thermal field emission gun, you always keep it on over a long duration, unless there is a special maintenance or something where you are bound to switch off the field emission system, whether it is within an SCM or within a TEM. You keep a thermal field emitter running. It can run over a period of 1 year, 2 years or even more, and typically when a thermal field emitter is running that way, the lifespan of a thermal field emitter is typically over a duration of 2 to 3 years. But in the cold field emitter, like in a thermionic emitter, you are switching on, you are flashing the filament, and every time you flash, you are kind of sharpening the tip once again, and you have a feedback loop to have a sustained emission. Your brightnesses you achieve can be quite high, and also you would have a longer FEG lifetime. There have been cases where cold field emitters have run significantly beyond 5 years or even 7 years, and it runs fine. That is because every time an oxide layer is formed and the vacuum is also maintained very well, you are kind of removing the top oxide layer by flashing. So that is about the lifetimes of field emitters and so on.